So now that we have looked into the typical image processing pipeline and some of the image parameters, both intrinsic and adjustable, let's move on into a very basic introduction about optics. Optics, as we saw just at the beginning of this class, is one of the important parts that constitutes a computer vision system or a vision camera. And there is at least one very simplified model for optics that is very, very useful when we have to process information about image or about video. So let's just have a small look about it. So as I said, the optical element of an image acquisition device is certainly one of the most important elements of those devices. Of course, we cannot underestimate the sensor, the color filters, the image pipeline, etc. But this is one of the critical in terms of quality of the image that we can obtain. Of course, that the optical lenses can be complex groups of lenses, in particular when we use variable zooming, for instance. But for most robotic image acquisition systems, we use a single converging lens at its optical interface, which looks like the one you see on this image. So this represents a lens with a certain radius, let's say, and one of the basic principles of this lens is if we assume that all sources of light come from infinity, so they are parallel between them and they are normal to the axis of the lens, then they will go through the lens, deflect, and all converge in a unique point called the focal point. The focal point is therefore one of the most important characteristics of a lens, and in particular the focal point distance, which is the distance between this point and the rotational axis of the lens itself. So in terms of formation of the image, here we are assuming that our sensor is located on this plane over here. This is our lens. The focal point will be there in the red, where the red spot stands now. And we are assuming we have an object in the real world, and the light that comes from this object goes through these lenses and then projects on the plane where the sensor lies. The most relevant measurements that we have to consider here is that we are assuming that the object we are observing is at a distance s1 from the lens. We are also assuming that our sensor is at a certain distance s2 from the same rotational axis of the lens. We are also assuming that f will be the focus distance. And if this lens is an optimal lens, then we can say that 1 divided by the focal distance will be the same of the sum of 1 divided by s1 plus 1 divided by s2. Of course, that if the distance s1 is much, much larger than s2, then we can assume in some circumstances that s2 will be very close to the focal distance. So if we move this object far, far away, this will tend to reduce the distance between S2 and F, which means they will tend to be basically on the same spot. From the assumption we made in the previous slide, we can derive one of the most used models that are used in image processing, namely in robotics. This model is called the pinhole model. It is a very simple and practical digital image processing technique or model to be used. And if we are using this model, then basically what we are doing is an approximation of what really happens within our optics. In this pinhole model, the lens is replaced by a very narrow opening, that's what we call the pinhole, and we assume that all the light that strikes our sensor goes through this small pinhole. And all the light that comes from the outside world goes through this pinhole and then projects into a certain point in our sensor. In this left image, we assume here that our Cartesian system is centered on our lens. This is the pinhole node. So if a point P in the external world is here at this point, there will be a light vector traveling in space, going through the pinhole and projecting on pixel Q on our sensor plane, which is, as you can see, on this rectangle. In this model, we assume that our sensor is exactly at the focal distance from the lens. So there is no difference between the distance of the focus and the distance of the sensor regarding the point of entrance of light, let's say. So therefore, we can apply here geometrically very simple techniques. And this point P can be described by a coordinate x1, by a coordinate x2 in a vertical sense, and a coordinate x3 in the x3 axis. And this will have a projection on our sensor, which can also be related to the axis y1 and y2. Of course, that any pixel along this green vector will project on the same point. And that is, of course, one of the limitations of a sensor that only has 2 dimensions, while our external world will actually have 3 dimensions. So by looking into this model, we can say that this pixel Q is equivalent to the projection of any point that lies along that green line. So we don't have any information of depth regarding the origin of this P source. If we do the same, but now projecting on the side, we can see here the x1. X1 in this case is this axis. And we can see here the x3, which is that axis over there. And we can see that any point lying on this green vector will be impacting the sensor on the same Q point, exactly as we saw on this left side. So, first of all, do not forget, this is a simplification of what happens in the real world. Second of all, this simplification can actually reduce the overload of the processing without degrading significantly the final results that we want to achieve. In particular, if we can add up some solution that can, in a way, compensate from problems that can be generated by the actual optical system that we have in our camera. And what happens in practice when we use a real acquisition system is that all lenses somehow introduces some form of deformation in the final image. We call this spherical aberration. And this comes from the fact that most lenses have an external spherical surface cut, which is easier to make than its proper shape. So normally, the lenses from the outside point of view are spherical when they should not be. And the result of that, we can have at least 3, which are the most important spherical aberrations that you can see on the 3 images in the downside of this slide. On the left, you can see what we call the barrel spherical aberration. It looks like a barrel actually, On the center, you can see the pincushion effect. It's like a net with a weight on the center. And on the right is a less common form of spherical aberration called the moustache distortion. By far, especially in low-cost visual systems, the barrel effect is the most common spherical aberration you can find in your system. And the important thing is that if you gather information from a known image, you can in fact obtain an equation from which you can compensate this effect, and from the original image you can generate another one where this effect can see almost neglected. That is, you can compensate the image in order to obtain an image that would correspond to exactly vertical straight lines and exactly horizontal straight lines. I don't want to go into many details into this slide, but you can see here on this image what happens when you have spherical aberration due to the wrong shape of the lens. What happens is that instead of having a single focus point, you have multiple focus points. And this in turn will result, for instance, in a barrel shift spherical aberration. One way to compensate for this is to use a previously known image that you can post-process, and based on that obtain a couple of coefficients that are here represented by K1, K2, and now depends on the level of this polynomial. But you can use basically these equations, which are known as the simplified Brown's distortion model. And here, just looking into it fast, XU and YU are basically the undistorted image point as projected by an ideal pinhole camera. And we can get that because we know in advance the kind of image that we are looking to. The XD and YD are the distorted image point as projected on the image plane using a specified type of lens that is on the sensor. And X0 and Y0 is what we call the distortion center, assumed to be the principal point. The principal point is the point where a vector of light which is normal to the plane of the center goes through the pinhole and hits the sensor. That the coordinates of that particular point is called the principal point of the pinhole model. The Kn are the radial distortion coefficient, and the R, which you see here, which is then power to 2, power to 4. Now it depends on the order of the polynomial that you are using here. The R is basically the radius or the distance between each one of the pixels in coordinates xd and yd and the central point of the sensor expressed as x0 and y0. So based on this and the knowledge of an image we know in advance, we can calculate each of these coefficients and then apply this transformation to, starting from the distorted image, obtain a non-distorted image. Moving on into a little bit higher abstraction layer, we would like now to shortly view something about camera parameters and perspective views. And I would say that in most of applications, namely in computer vision and in robotics, what we'd like to do is to extract from the frame image information regarding the external world, because in this sense, the vision system acts as a sensor for the robot and allows the robot to perceive what is going around itself. These applications, of course, may include, for instance, the determination of a certain distance of a point represented in the image. The image is, in this case, the sensor of our acquisition system, when evaluated in the real-world coordinate system. Of course, I can only determine the exact coordinates in the world system if I know also at least the plane in which this original point lies. Otherwise, I only get a 2D image, and it's not possible to extract 3D information from a 2D image. So moving on from the origin will be the object coordinates, which are in the world coordinates, so in 3D. We have the world coordinate system, which is also 3D and is based on this Cartesian system that we extract the object coordinates. Then we have the camera coordinates also regarded to the world coordinates. And then we have our first limitation, the image plane coordinates, which are only 2D. Inside the image coordinates, we also have the pixel, each of the pixel coordinates, normally expressed in 2D, also X and Y. And therefore, based on information we get here and some knowledge we may have from the external world, we can perform geometrical transformations that can accommodate the camera internal parameters and the geometry and its position and posture in the real world. That is, if I'm looking into something within a certain world coordinate system, I also have to know what is the current position of the camera that is looking into this world. If it's looking upwards, it's seeing something in the world. If it's looking downwards, it's seeing something else. If it's looking from a certain plane, which is not parallel to any of the three main planes, then we have a particular posture, and we have to know something about that posture if you want to extract real information from the external world. One very important technique used when processing information from an image, trying to extract information about the world, is to use a type of coordinate system called homogeneous coordinates. Let's take, for instance, a single point in the world coordinate system, x, y, and z. We can represent this just as a single vector, or we can add up a fourth element. In fact, this fourth element is an element which is a multiplication factor applied to each of the x, y, and z components. The advantage of using homogeneous coordinate systems is that you can represent any point in space by a multitude of equivalent matrices, since the Cartesian coordinates, the Cartesian are x, y, and z naturally, can be recovered from this homogeneous coordinate system by dividing each coordinate by the factor w. This has two extra advantages, one of which we'll look in the next slide, and the first one is that this use of homogeneous coordinate systems allow us even to represent any point in a plane which is at an infinite distance from the origin. Otherwise, you could not, if you want to represent here a point xyz which is at infinite distance, it's not possible. But if you use, for instance, an xyz, any xyz you want, and you use a w of 0, it means that to obtain the original point, you have to divide all of the three coordinates by 0, therefore generating a point at infinity. But using the homogeneous coordinate matrix, you can actually obtain a vector. Therefore, you know that the point is at infinity, but you know the vector from the origin to that point. And with a simple Cartesian system, you cannot do that. So using homogeneous coordinate systems is quite common, not only because it allows you to define any vector to any point that lies at infinity, but as we will see, also because of another reason. In order to further understand the utility of the homogeneous coordinate systems, let's first look at the two most important geometric transformations that we may want to apply into a certain point in space. First, let us assume that we have a vector defined by 2 points in any Cartesian system. Point AN in this case is defined by this vector. and Cn represents the point which is the pinhole coordinates that we have in our pinhole model. The product of matrices that you see here is the required matrices to generate a rotation among the three axes x, y, and z. And this is the matrix for rotation around the x-axis, where theta is the angle of rotation around that axis. Here you have the matrix for the rotation around the y-axis, and here is the rotation or the matrix for the rotation around the z-axis. As I said, the original coordinates regarding the pinhole Cartesian system are defined by ax, ay, and az in a 3D dimension, and the application of the product of these matrices will result in a second point, dx, dy, dz, rotated by the angles that you define in each of the three axes. So rotating a certain vector in space is one of the most important Cartesian transformations that we may want to do in image. A second one is the translation vector transformation. In the translation, there is no rotation, but you simply move a point P from one point in space, from a set of coordinates in space, to another set of coordinates in space. And this transformation can be defined by using an homogeneous transform by this equation that you can see here. So Px, Py, and Pz is basically the original point that you want to translate. Then you have here the translation matrix. As you can see, is an homogeneous matrix. In terms of these three components, you have a unity matrix, a 3x3 unity matrix, and the W value in this case is also 1. Vx, Vy, and Vz are basically the values that you want to add in each of the three axes. So this is a translation in x, in y, and in z. The result, of course, will be the sum of Px plus Vx, Py plus Vy, and Pz plus Vz. And this is basically a translation in space of one point to another. So basically, if you see, this is the homogeneous representation of the translation matrix. And what is interesting here is to look that to apply an homogeneous solution for here, you have a unity matrix in this area. So as a result, we can in fact do something which is interesting, is that you can combine the rotation matrix that you have seen in the previous slide with the translation matrix and apply a simultaneously rotation and translation geometrical operation upon any point in space, where these are the coordinates of the original point in space, and these are the coordination of the resultant transformation in space. Of course, this is a vector. This is also a vector, also represented in homogeneous coordinates. And the fact that we are using homogeneous matrices allow us to combine both kinds of geometrical transformations in a single matrix. And this is the second and also more important consequence of using homogeneous coordinates instead of Cartesian coordinates straight away. From the original discussion, what should start to be apparent is in order to obtain real-world information based on a 2D image on a camera, you have to perform a set of geometrical transformations, because the camera will be located in relation to the world coordinating system in a certain angle, in a certain plane. There are also some manipulations of the image that we have to perform due to, for instance, the distortion of the lenses, as we said, and therefore it means that in order to get relevant and as precise as possible information from the original image, we have to deal with a set of parameters that in the end will determine what exactly what we have to do from the mathematical point of view in order to get the final information we can actually use. In that perspective, we can say that the camera parameters are normally divided into big groups. The first one is what we call the extrinsic set of parameters, and the extrinsic set of parameters are defined based on the location and orientation of the camera reference frame with respect to a known world reference frame. So the extrinsic means that they lie outside of the camera, has to do with the position of the camera and its orientation in regard to what we consider to be the world coordinates reference frame. There is another group of parameters called intrinsic parameters. This has nothing to do with the relation between the camera and the world outside, but are the parameters necessary to link the pixel coordinates on our sensor and an image point with the corresponding coordinates in the camera reference frame. And this has to do with aspects related to, namely, the optical system that we are using at a certain point. So the intrinsic parameters can be measured, can be quantified, and once obtained, you can apply the transformations necessary to obtain a set of coordinates from the perspective of the formation plane, that is the sensor of the camera. The extrinsic parameters have to do with the way the camera is positioned in relation to the world, and therefore it determines what rotation and translation transformations we have to perform in order to obtain information about a certain point in the outside world. From the two groups of parameters, let's start by looking first at the camera intrinsic parameters. These intrinsic parameters are defined as a matrix of the form you can see here. A is the intrinsic parameters matrix. You can see that some of the values in this matrix are actually 0, or in this case 1. And the most important ones over here are the alpha, x and y. Alpha, x and y are in practice the focal length that you are used, and are expressed in the form f times mx and f times my, in which f is actually the focal distance. Of course, this only makes sense in the case where pixels are not square. If pixels are square, then mx will be the same as my, and in practice you can consider this one, which means that these two values in this intrinsic parameters matrix will be the focal distance of the camera, which is the most common case, let's say. This alpha value here, normally this represents one phenomenon called the skew coefficient between x and y. It has to do with the efficiency in the production of the sensors. Normally we can consider this to be 0. And finally, the U0 and V0 represents the principal point, which ideally will be in the center of the image, but in some situations, due to misalignment between the lens and the sensor, can be slightly on the side. So I recall that the principal point is the point that is hit via a light vector, which is normal to the sensor and goes through the pinhole. So that light vector will hit the sensor, ideally on the center of the sensor, but sometimes there may be some misalignment, and in that situations the U0 and V0 will determine exactly which is the pixel that represents the principal point. So once we know this, we know the focal distance, we know the principal point, which means that we know everything that we need to perform the geometry at the level of the pinhole simplified camera model. Of course, that if there is lens aberration, on top of this, we also have to apply the equations to consider the possibility to correct for that particular aberration. The other set of parameters, as I said, are called the extrinsic parameters. Here you can see a coordinate system that represents the world coordinating system, and we assume that this point P is represented here in the world coordinating system by this vector, and here is the coordinating system that represents the plane of the sensor of our camera in relation to the coordinate system of the world. So typically this coordinate system will represent a translation and a rotation from the original world coordinating system. If we know this transformation matrix, we know exactly how our vision system is positioned and oriented towards the world coordinating system. Of course, at the same point, in this case, will be seen by our camera system in a different perspective, naturally. And of course, we will have to recalculate based on the information, the 2D information we get on the camera, to recalculate what would be the position of this point in regard to the world coordinating system. To close this up, just to note that the extrinsic parameters we have just discussed does not reflect the position of the camera in regard to the world coordinating system. We know that this position of the camera results from a translation and rotation, but the extrinsic parameters in fact represents the position of the origin of the world coordinate system expressed in coordinates of the camera-centered coordinate system. There is, in fact, when I see a point in the sensor of my camera, I want to know by this transformation extrinsic parameter matrix where this point lies. In fact, it will lie on a vector because we don't have 3D information in the camera, but where this point lies in relation to the world coordinating system. And in that way, if I know that, for instance, that point lies on the floor, and if I know what exactly is the plane of the floor, then I have enough information to extract the exact coordinations of that point based on information I gather from my camera. So the transformation that we have to apply to the original information in our image is the one that results from this equation, where C is the camera position expressed in world coordinates. Still referring back to the pinhole camera model, and knowing the rotation and translation geometric transformations that represent the position of a camera related to the world, and also A, in this case A represents the camera intrinsic parameters, we can therefore, based on any triplet representing a point in the world space, we can obtain exactly what would be the pair UV, the pixels U and V, on our sensor plane that would result by the observation of this world model point. And in that sense, we can map or do a direct map from any point in the world to any pixel in the image, of course, within the field of view of that particular image. If we want to do the opposite, we have to invert the application of these matrices to obtain the vectors on the real world that correspond to a certain point in our observation plane. Finally, and although this is clearly not the scope of this class, let me just show you a couple of examples of simple image processing tasks. So when we come up to this point, it means that everything we have discussed previously have already been established. That is, we know the intrinsic parameters of the camera, we know the characteristics of our sensor, We know what the world coordinate system is. We know the pipeline and the process pipeline that are used to generate the final image. And in the end, we can obtain at least a vector corresponding to each of the pixels that lie on our sensor. Based on that information, we can then process, because now we are at the computer level, not at the camera level, we can process the information and extract some extra information that can be relevant. And what is going on the next slides is basically a couple of examples of practical applications of image processing tasks. So simple examples of image processing tasks. One which is very common is called spatial filtering. In spatial filtering, basically what we are doing, why we call it filtering, is because we do it in frequency. Frequency means the variation of luminance, of chrominance in an image, in a 2D image in this case. What happens is we can apply a filter in the frequency domain by multiplying the frequency domain image by a certain kernel. The problem with doing this is that you have to obtain a frequency domain image, which is a heavy task work. But by definition, the multiplication in the frequency domain is equivalent to the convolutional in the space domain. And since the image is symmetric, applying a convolutional matrix is a rather straightforward method for applying filters. Filters in this case will be, for instance, low pass or high pass filtering. There is techniques through which you can blur an image, for instance. It means that it goes through a low pass filter. You remove all the high frequencies features of the image, or a high pass filtering where you highlight the fast changing aspects of the image, reducing maybe the slow features. There are very large sets or kernels for spatial filtering that you can find in normal processing image applications, through which you can do a lot of nice and neat tricks, but most of them will normally will result not in only on a new image, will result on a new image and not on an external result. Also, you can apply, for instance, convolutional matrix filtering for doing things such as edge detection. As the name implies, this means that you want to look at an image and detect the edges that are present on that image. For instance, in this case, what we are seeing is something similar to a road. This is a zebra walk pass, and the idea is to extract the limits between dark and white areas. And on the right you can see exactly what results from the extraction of the edge using, in this case, a Canny filter, which is also a combination of convolutional matrices. So this is one of the possible examples of imaging processing tasks. Another technique which is quite common and useful in different applications is called segmentation. Segmentation is a way of reducing the original information by separating informations based on luminance or based on chrominance. On the top, for instance, you have an original image, and by defining a certain threshold, you isolate the areas of the image which are below that threshold, in this case the darker areas, while the lighter areas are kept dark in this case. In the bottom image, we are using a chrominance filter that allow us to, for instance, highlight the green parts. So everything that looks green here actually is transformed into green in the filtered image. Everything that looks white is actually transformed into white over here. and also everything that looks black, as you can see here, is transformed into a true black. In this way, you can reduce significantly the number of segmented colors. In this case, for instance, in this example, we are using actually 5 different colors to segment different objects based on their color. For instance, there is a ball over here, there is 2 other balls over there, and we can use this segmentation technique to isolate that particular balls because they are different from the background, which is typically green, as you can see. So color segmentation is also a technique which is very useful for certain areas of application. In this example, this is the case of the soccer robots, so the robots that play soccer or football. And this is a technique for isolating and identify the main objects on the image. Of course, that this only works, by the way, if the white balance of the image is correct. If there is a wrong white balance, the chrominance filter will not work. Finally, if we move into something that we call artificial vision, there are, of course, much more complex processing techniques that allow more complex results, but of course, we don't have space here to cover these techniques. Examples of those could be extraction of morphological operators, image descriptors, pattern recognition, etc., etc., etc. There is a simple example here. In this case, this object in this cover is identified, and there are a set of aspects which are extracted and compared to a very large library of images in order to try to classify, in this case, to recognize the pattern of the object we are looking at. And if everything goes okay, in the end, our software could say that this is a bottle of a certain type of juice, a very well-known brand, let's say. If we look here, this is probably a tin of tuna, for instance, and probably this would be tomato juice. I don't know. But in this case, we are clearly on the level of abstraction completely different from the ones we have discussed so far. Finally, if you are interested in these areas, be it at the lower level of abstraction that we have discussed a little bit more thoroughly, be it at the image processing level, be it at the artificial vision level, the one that we only just mentioned, you can look further into some of these references you can see in this slide. And also, depending on the area of work that you will be doing in the future, this may come up at certain point in your way, and who knows, you may come out to be an expert in the field. So that's all from me for the moment, and see you.